Hi. In this lecture, we will talk about stabilization of the advection-diffusion equation with the finite element method, and specifically, we'll talk about the Petrov-Galerkin methods and work our way towards the famous SUPG method in solving the advection-diffusion equation. So let's consider the 1D advection-diffusion again. We'll start with the 1D equation one more time, and then we'll talk about the multidimensional transport. So in Galerkin finite elements, we talked about the shape functions that we use to approximate our solutions over each element. These shape functions are similar nature between the weights W that we multiply by the equation and integrate, and the child functions U, which are our solutions. So that's the Galerkin. The idea behind Petrov-Galerkin is that what we're going to do is that we're going to be using different shape functions between the weights and the child functions. So, for example, in this picture that you're looking at here, in this 1D case, assuming that the flow is from left to right, meaning that the velocity A is positive, if you look at two consecutive elements, it could be the case that you might want to weight or define the shape functions for the upstream elements. That's element E. You might want to define these shape functions such that they are weighting the solution more on the upstream element compared to the downstream element. So this is what this picture here tells you. And this is what refers to as the idea of upwinding. This is kind of similar concept, because by doing this, what you're doing is essentially just similar to upwinding that we talked about in the context of finite difference. If you remember, we took the points, the nodes upstream in defining our finite difference stencils. And here we're doing the same thing. We're kind of like looking at the upstream element, similar to upwinding in finite element, and we're weighting that element more. So then if you come to the shape functions, if you write your shape functions N for your child functions U or your solutions, they look something like this. They're linear functions. And effectively what you're doing is that for the weight functions, you're taking the same shape functions, but then you're modifying them by these so-called bubble functions, which are these quadratic terms that you're adding to your weight functions, and you're essentially adding to the element upstream, and you're subtracting from the element downstream. So this way you're kind of creating these types of shapes, okay? And you're now in a Petrov-Galerkin finite element framework where your shape functions are different for your weights and your solution. So then if we go to we can use this definition, and we can move on to the weak form that for the 1D equation that we've previously derived. Here I'm ignoring the boundary term, or really assuming that the boundary conditions are all Dirichlet boundary condition. If you plug in these shape functions and the typical finite element approximation, and you integrate this equation, you can show that this is what it comes down to in this 1D problem. As I mentioned before, finite element becomes very similar to finite difference in 1D. And this is the form of the equation that you will get by using these modified shape functions for your weights. Okay, you'll get some equation that looks like this. And this parameter beta that you're looking at, so this is the beta controls how much more you put a weight on the upstream element. So it's a free parameter. And it turns out that in this specific one-dimensional test case, if you want to avoid numerical oscillation, the beta value that you choose has to be greater than a certain critical value given by this formula, which depends on the grid Peckner number. So remember the grid Peckner number, which was the velocity A times h, the mesh edge size, divided by 2 times the diffusion coefficient. So this is how we can avoid numerical oscillation. Okay, so in this example here, what you're really seeing is that an alternative approach or alternative view really to what we already presented with the 1D finite difference method. So now we're putting it in the context of finite element and Petrov-Galerkin frame. Okay, great. Now let's start doing this a little more rigorously from the beginning. So What we're going to do now is that we're going to revisit the 1D advection diffusion equation, and we're going to slowly work our way up towards the SUPG method. So this is the so-called Streamline upwind Petrov-Galerkin, the SUPG method, which is a very popular approach for doing finite element for convection-dominated fluid flow problems. This was first introduced in the 80s by Tom Hughes, and really it was around that time when finite elements started to become popular for fluid mechanics. So prior to that, prior to the SUPG approach from the 80s, finite element was mainly just used among the solid mechanics community. And after this SUPG method by Tom Hughes, it started to gain popularity in fluid mechanics community. And of course, arguably still finite element is much more popular among computational solid mechanics folks compared to us in CFD, right? So most people who do computational solid mechanics use finite element, but that is certainly not the case in the fluid mechanics community, where other methods like finite volume are probably even more popular. Okay, now let's talk about this SUPG method. So we're going to start with the 1D equation and slowly work our way towards the concept of this SUPG approach. So the easiest way to think about stabilization is to think about it in terms of numerical diffusion or numerical dissipation, artificial diffusion, right? All these different names. So really, we can think of it this way. So we can take the advection diffusion equation in 1D, A partial U partial X equals the diffusion coefficient times the second derivative of U. And what we're doing is that we're just adding to the diffusion coefficient. So we have the physical diffusion coefficient D, and we are adding a new artificial diffusion called D bar. So this is basically the equation that we have. And we're going to define D bar by equation 1 here. So we're going to define it as equal to beta, a free parameter, times A, which is the velocity, multiplied by h divided by 2. So this is similar to what we saw previously, but with the coefficient beta added. And this is a consistent, as we previously talked about, this is a consistent way to add artificial diffusion. Why? Well, first of all, because it scales with h, my mesh h size. So the smaller the h is, as I'm doing my mesh refinement study, the less the effect of artificial diffusion becomes, which is desired. Second, it scales with the advection velocity A. So therefore, as my velocity becomes smaller and smaller, so I have less and less important advection, but less compared to diffusion, the effect of the artificial diffusion will become smaller and smaller. And then there's a free parameter beta that I can arbitrarily set to control the amount of artificial diffusion that I want to have. Okay, so if I consider this equation, if I can derive the weak form. So this is what we've done multiple times by now. So I'm just doing integration by parts on the diffusion term. And I'm assuming all boundary conditions are Dirichlet, so I have no surface term here. So this is my weak form for this 1D equation. And it turns out that you can prove that the optimal value of beta in 1D is given by this formula. So cotangent hyperbolic of the grid vector number minus 1 over the grid vector number. So if you select this value for your free parameter beta for the amount of artificial diffusion you're adding, which is actually depends on the grid vector number, then you can get the best result. Essentially, you can get nodal exact solutions. And also, if you just select beta equals 1, which is what we've previously seen in our previous lectures, you're going to get the full upwind finite difference. So it's in 1D, of course. In 1D, you're going to get something equivalent to the upwind finite difference. Okay, great. Now, if I select this equation for my artificial diffusion, equation 1, let me plug it into equation 2, which is my weak form, and let me collect the common terms. This is the equation that I get. So this is really what my weak form is if I add this artificial diffusion to my diffusion coefficient. Now, if you pay attention to this new weak form that we have, and you compare it to the Galerkin weak form, which is what we had previously, you're going to see that it looks exactly the same. So this term is exactly the same. You have the advection term, but now what you have here is that you have a new weight function or a new test function being multiplied only to your advection term. So it's like you're only modifying the advection term, but you're not modifying the diffusion. And this is the new weight function for your advection term. W tilde is the old weight function plus this added term, which involves this derivative of the weight function. So that's really what happens. By doing artificial diffusion, by simply taking my governing equation, which is up here, and simply adding artificial diffusion in a consistent manner by this equation, as we argued, we arrive at a weak form that looks identical to what we previously had, with the only difference that the weight function corresponding to the advection term is now modified. It has this part, which is the extra new part. Now, what is the issue with this approach? The issue here is that, this weak form is really no longer consistent with my strong form of the equation. It's no longer consistent with my PDE. Because if you remember how we derived weak forms was that we took our PDE, the strong form, we multiplied the PDE by a weight function and we integrated. There was nothing wrong with doing that, right? This is just, there's nothing wrong with that. But now, essentially what we're doing is that I am multiplying my PDE. I'm multiplying each term with a different function W and then integrate. This doesn't sound right. It's not, that doesn't correspond to the same equation anymore. So it's not consistent, right? So, well, so really what we have to do is that we have to think about how do we make this consistent. So we'll talk about that later in this lecture. But for now, one idea that comes to mind is that, okay, this is the W tilde that I found. Why don't I go ahead and just this W that I have in my diffusion term also make that W tilde, right? So change this W that I have here to be this new W tilde. By doing that, it's like as if I had multiplied my governing equation by W tilde instead of W in a consistent manner. So now things are going to be consistent. Okay, so I can change this W to W tilde and have a consistent weak form. There's one thing you have to be very careful when you do that, and that is when you use linear shape functions. So if you're using linear shape functions, which is actually pretty common in finite element, what's going to happen is that as soon as you make this W here W tilde, so this is W tilde, right? You already have first derivative here. W tilde also has a first derivative. So what you're going to get by changing this W to W tilde, you're going to get second derivative of W. So what does that mean? If you get the second derivative and you're using only linear shape functions, the second derivative becomes 0. The second derivative of a linear function is 0. So that will just go away. So essentially, even if you define this in a consistent manner, meaning that just change this W here to be W tilde, partial x of W tilde, if you are using linear finite elements, you're going to get the same things. Essentially, you're still not consistent if you're doing linear finite elements. Okay, great. Now, let's start talking about the multi-dimension case. So far, everything was 1D, but, we're really, when we talk about finite element, we're really interested in 2D and 3D problems. So if we go to 2D and 3D, the idea is that, okay, we're still going to think about artificial diffusion, kind of, but now we're going to only want to add diffusion along the streamline direction. So this is where the name streamline, upwind, Petrov-Galerkin, or SUPG comes, because now we want to only add the diffusion along the streamline direction where the velocity vector is pointing towards. Therefore, we're going to define an added diffusion in a tensor form that's anisotropic. So we're not going to be using an isotropic diffusion, but rather I'm going to be adding diffusion or artificial diffusion that is different in different directions. Essentially, I want my artificial diffusion to only be added along the streamline directions, which is where advection is happening. I don't want it to happen perpendicular to where advection is happening because that's not desirable. Okay, So how do I define it? So I define it as a simple scalar d bar times this outer product between my velocity vectors. So the outer product of velocity, so AIHA, the outer product of two vectors gives you a tensor. And then you can normalize by the velocity, the magnitude of the velocity, the norm of velocity to the power 2. Okay, so you have a scalar. The norm of velocity is also a scalar, so it's just normalization constant. And then this outer product between your velocity vector gives you the direction. So essentially, this outer product is figuring out the streamline direction for us. This is normalizing the velocity because we don't care about the velocity magnitude, right? We're just interested in the velocity vector direction, right? This is just a direction problem here. And then the amount of diffusion we add, the amount that we want to add is controlled by this scalar d bar. Okay, as an example, if you look at this unidirectional flow where your velocity vector A is just simply 1 and 0, so purely in the x direction, if you plug in this A into this formula, you can easily calculate the norm and do this outer product. This is the diffusion tensor that you get. So d bar ij, my artificial added diffusion tensor, is a d bar scalar that I need to define and or select times this matrix that you see here. And this is, you can see it only has a component in the 1, 1 direction. So I really just have diffusion added in the streamline direction, which is the x direction. Fantastic. Okay, great. Now let's continue with the advection-diffusion equation in multi-dimensional form in vector notation and kind of see how we can incorporate these concepts into the vector form of the advection-diffusion equation. So we already took this equation in previous lectures and we derived this Galerkin approximation, essentially multiply this equation by the weight function W, do integration by parts on the diffusion term. This is the weak form that we previously derived. So here, again, I'm assuming all the boundary conditions are Dirichlet. So I have no surface integral term. Now, what I'm going to do, similar to how we did the last section, I'm going to just take my diffusion coefficient that was previously D, add this new D bar, this new artificial diffusion tensor that I defined up here. I'm going to add it to my previous diffusion coefficient. So the previous diffusion coefficient really here that you see here is really multiplied by identity matrix, so the identity tensor. And then when you do the math, you can kind of see that it shows up like this. So if I take D times I, the identity matrix or tensor, plus my new artificial diffusion tensor that I defined, I'm going to get my modified diffusion coefficient, which I'm going to call D tilde. So my weak form looks exactly the same, but instead of D, I have D tilde that's defined as a combination of the physical diffusion plus added artificial diffusion. So now let's take a look at this term, this diffusion terms, Laplacian term in my weak form and see if I can simplify it. So I can actually show that this term could be simplified. So if I plug in the definition of d bar, so this is how I defined d bar, okay? So if I plug in the definition of d bar into this term and simplify, I can show that it will look something like this. So my integral will now look, essentially it will look like the exact term I had before, the physical diffusion coefficient, grad W dot d grad U, the term we previously had in our Galerkin FEM, plus I'm going to have this extra term. This extra term that involves d bar, the free parameter I had for how much diffusion I want to add, divided by norm of A, norm of velocity squared, times A dot grad W. So this is like an advection term, but applied on the weight function, times my regular advection term, A dot grad U. Okay, so this is going to be my new term that's going to pop up. Okay, so if I plug these two into my weak form and collect the terms, this is the final form of the equation that I get. So I arrive at something like this. And this is kind of similar to what I arrived in the previous section for the 1D case where I added artificial diffusion. You can see my the regular typical diffusion term that we have in our weak form is remaining the same. This is based on the physical diffusion coefficient. And then we have our A dot gradu term, the typical advection term. But instead of being multiplied by W, our weight function, this is now modified. This is now multiplied by a modified weight function, which I call W tilde. So essentially, by weak form, the diffusion term is the same. But for the advection term, my weight function has been modified. Okay, and this is the modified weight function for my advection term, which is the old weight function plus this extra term, d bar, the amount, my free parameter that controls how much artificial diffusion I'm adding, my normalization of velocity, and then A dot grad W, another advection type term, but now applied to my weight function. Okay, so this really brings up the same problem too, right? I'm only modifying my weight function on the advection term. So this is not really consistent, right? Because it's like I'm only I'm multiplying or weighting every term differently. So this gives us a weak form that's not consistent, similar to the one-dimensional case. Okay, so now let's see how we can turn this problem into a consistent weak form. So now we want to have a weak form that's consistent, okay? So if I go back, let's consider the advection diffusion equation. Now I'm going to also add the reaction term, okay, to write more general form. Now I can define the residual of this equation, okay? So if I bring all the terms on one side, I know that this has to be equal to 0, right? This is the residual of my strong form of my PD. So the residual in this case is this differential operator, L, which is basically the advection and diffusion operator, minus my known source term, S. So for the weak form, I already derived this weak form. So these 4 terms that we already derived a couple of lectures ago. So we derive the weak form. So I'm going to take the same weak form I previously derived. So if you remember, we defined these A, C operators, and then we had these inner products when we derived the weak form for this equation. I'm going to have the same weak form, but now I'm going to add a stabilization term, another integral equation that I'm going to add now in a consistent manner. I'm going to make sure that this stabilization, this added integral equation, scales with the residual of my PD. Okay? And that's R of U. And why am I doing that? Because if I make this scale with the residual of the PDE, I can be sure that if I'm doing a good job of satisfying the PDE, so if RU is almost equal to 0, as I'm, for example, refining my mesh, doing a better job approximating my PDE, the effect of the added stabilization vanishes. Okay, so as my residual approaches 0, this effect of added stabilization or artificial diffusion, whatever you want to think about it, its effect becomes smaller and smaller, and it vanishes. So that's the consistent. Now, the tau parameter is a free parameter that I'll talk about in a moment. And I have this P function, P as a function of W, my weight function, which inspired in SUPG method, inspired by what I derived in the last section. So if I go back, inspired by this derivation where this A dot grad W term pops up, inspired by this derivation, I'm going to define this to also be A dot grad W. Okay. So here I'm going to have A dot grad W, similar to what we derived in the last section. Tau is my free parameter. So similar, tau is kind of like similar role as this D bar here. And then I have the residuals for consistency, all multiplied by 1. So in the last approach, if you want to be similar to the last approach, it's like you're choosing tau D bar over norm of A squared. So this choice of tau is essentially inspired by what I just derived in the last section. Okay. And D bar is your free parameter, which is in this case, which controls how much artificial diffusion you want to add. And in 1D, this is how we define it. And we're actually able to show that for a certain choice of beta, this was exact. We can only do that for 1D, but that's good because it can inspire us in defining this in 2D and 3D problems. So we can choose this tau inspired by what we derived in the last section, and we can choose this value for d bar inspired by what we did in the 1D problem. Okay, and you also talked about what choice of beta gives us the optimal value. Okay, so if I put everything next to each other, this is my new weak form that I have. So it's the same terms we previously had for the advection-diffusion reaction, but this circle term is the new stabilization term that I have, which is, it has the A dot grad W, kind of like an advection term acting on the weight function, multiplied by tau, a free parameter, multiplied by the residual of my PD. This is the residual of the PD. And there are many different forms of tau. So this is one form here that we just talked about, modified by what we did in 1D, but there are many different forms of tau defined in the literature. And this is one of those popular choices that I'm writing it here. So this is, this formula. So this expression raised to the power -1/2. So it depends on A, the velocity magnitude, D, the physical diffusion coefficient. You have 2, 9, 4, these coefficients raised to the power 2 here. And H here is the mesh edge size. So you define it to be dependent on the mesh edge size. Because if you remember, that was the same case when we defined optimal value for beta here. We also talked that that depends on the grid vector number, which is really the mesh edge size. So here the mesh edge size also appears. So this is just one choice for tau, but we can have different choices for tau as well. So you will see different choices for tau in the literature. Okay, so this is what we talk about when we talk about the SUPG method. So this is the final form of the SUPG, the FEM-based SUPG method. You can still have one criticism of this equation. If you pay attention, you see when we add the residual, what do we have here? We have the diffusion term in its strong form that contains a second derivative. So if you are using using linear finite elements, okay, so linear shape functions, which again are common, then what happens is that this term just becomes 0. Okay, so this term is essentially 0. So really, you don't quite have the consistency. There's a little bit error here. But it turns out that that effect is not that concerning because we're really using this for advection-dominated flows anyway. So this term, it can end up being, less important, right, compared to the advection. This term could be less important. So, it's kind of okay. Now, there are cases where that's not the case. One example is when you're doing mass transport in near wall regions. So if you're dealing with very thin concentration bound layers, you're doing near wall mass transport. So this is advection diffusion for very high Pector number and high Schmidt numbers, where you get this thin boundary layer problem, or just high Pector number, really. So you might need more advanced versions of SUPG stabilization and more considerations about that. So I encourage you to read this paper, one of our papers from, I'll provide a link to the description box. And if you read this paper, you can see an examples of all these things we talked about related to stabilization. And also you'll see more advanced versions of stabilization for the advection diffusion equation. And you also see more challenges that arise when you go to near wall mass transport. And you need to think about more things when you're solving mass transport in the near wall region with finite element method. Okay, thank you.